Hello everyone, we have already finished discussing our JEE Advanced 2025 paper 1. So this video onwards will start with paper 2. There are total 4 questions in section 1 and those are single option correct questions. So let's see the first question and you'll be able to see the questions on the screen. As I read out the question from this iPad, you'll be able to see the questions on the screen. So let us see the first question. A temperature difference, question number 1. A temperature difference can generate EMF in some materials. Let S be the EMF produced per unit temperature difference between the ends of the wire. Sigma is the electrical conductivity and kappa the thermal conductivity of the material of the wire, taking M, L, I and K as dimensions of mass, length, time, current and temperature. Respectively, the dimension formula of the quantity Z, that is S square sigma by kappa. You have to find out the dimension for this. So see, whatever mentioned, that is S, that is the EMF produced per unit temperature difference. Sigma, that is electrical conductivity, and the final one is kappa, that is the thermal conductivity. So kappa is thermal conductivity. Kappa is thermal conductivity. Nobody remembers the dimensional formula of S, sigma and kappa. So whenever this kind of questions you will get, you have to do it on the spot. So you have to rely on some equation that you know, which you can make with this, and then you can derive the dimensional formula for this on the spot, because just remembering this formula is useless. There is no point of remembering the dimensional formula of this. So just one formula is enough to derive the dimension of this quantity. So S is EMF per unit temperature difference. So what will be the dimension for S? So see, EMF is, let's say, V, volt, by temperature T. So S equal to V by T. So S also you can write QV by QT. Q is the charge which you multiply on the numerator and the denominator. So see, QV will give you the dimension of energy, because electron volt is a unit of energy. So QV also energy. So you can write the dimension of S is actually the dimension of QV, that is the dimension of work, mL square e to the power minus 2, by the dimension of Q. Q dimension is I into T, or the current into time. I into T will write, and here the dimension of T, that is temperature, is K. So we can find out the dimension of S, that is M L square T to the power minus 3, I to the power minus 1, K to the power minus 1. We got the dimension of S. Now electrical conductivity, which formula we remember? We remember J, that is sigma into E. What is J? The current density is I by A, or current flowing per area, per unit area. Sigma is electrical conductivity sigma. E is electric field. So electric field I can write electric field as F by Q also, force per unit charge, force experienced per unit charge. So the dimension of sigma, that is becoming Q into I by F into A. A is the area, F is the force, Q is the charge, I is the current. So dimension of Q will be IT into I by F, dimension you know, mL to the power minus 2, area dimension is L square. So you can write the dimension of sigma to be m to the power minus 1, L to the power minus 3, T cube, I square. That is the dimension of sigma. And thermal conductivity, the final one is thermal conductivity. You have to find out. Thermal conductivity, which equation you know? You know the Fourier's 1D heat conduction equation. That is Q, that is kappa into area into dt dx, that is the temperature gradient, into time. Now the dimension of the dimension of Q, that is the heat or energy, by area, temperature gradient, time. Now Q is heat, so it is a kind of energy. So ml square raised to the power minus the dimension will be area, dimension will be L square, dt dx, gradient of temperature gradient. So it is K by L, and of course time is T. So you can write m, L will cancel out ultimately. So ml k to the power, okay, ml t to the power minus 3 k to the power minus 1. That is the dimension of kappa. Now you got all the dimensions. Now I have to find out the dimension of z, which is s square sigma by k, or kappa. So dimension of z will be the dimension of s into sigma by kappa. So s dimension we have found out, that is m l square raised to the power minus 3. So we'll just square it. We'll write m square minus 6 I to the power minus 2 k to the power minus 2 into sigma. So now this part is over, so we can erase this part. Sigma I can write m to the power minus 1 L to the power minus 3 T cube I square by kappa. Kappa is m L T to the power minus 3 K to the power minus 1. Now this I have to simplify. So m to the power minus 1. So this will ultimately cancel out. So m dimension is becoming m to the power 0. L square L to the power minus 3 L to the power. So ultimately this L is also becoming L to the power 0. So T I have to see. T I am getting T to the power 6 minus 6 is there. So T to the power 0. K is the temperature. Temperature I will see. It is becoming K to the power minus 1. Now I to the power minus 2 or I square. So it will be I to the power 0. So finally I am getting everything, I am getting to the power 0, and only thing that is there, that is k to the power minus 1. So the dimension of z will be m to the power 0, L to the power 0, T to the power 0, I to the power 0, k minus 1. So which is matching with option B. So see, this question is just given to waste your time because it is a very lengthy problem. So you have to be very thorough, and any of these steps you cannot make any mistake. So you cannot afford to make any mistake in any of these steps. So ultimately you will get the answer correct. Option B is the correct answer. So let's solve question number 2, and to solve this question you have to use your imagination. Because we are going to use the figure 2 which is given, not the figure 1. Figure 1 you have to imagine that figure 1 is there with figure 2, because figure 2 is the top view given. Now let us read the question. It is given that two coaxial conducting cylinders of same length L with radius root 2r and 2r are kept as shown in the figure 1. The charge on the inner cylinder is capital Q. The outer cylinder is grounded. The annular region between the cylinders is filled with a material of dielectric constant kappa equal to 5. Consider an imaginary plane of the same length L at a distance capital R from the common axis of the cylinders. This plane is parallel to the axis of the cylinders. The cross-sectional view of this arrangement is shown in the figure 2, that is the top view of course. The flux of the electric field through the plane you have to find out, and epsilon naught is given the permittivity of free space. But right now the region between the cylinders is filled with the dielectric constant kappa equal to 5. So we have to use epsilon naught into 5. Okay, let us see this question. Question number 2. Now we'll draw the top view of the question. So this is the inner cylinder. Now we can draw the outer cylinder like this. The radius of the inner cylinder is root 2r, and the radius of the outer cylinder is 2r. There is one plane at distance capital R from the center of the two cylinders. You have to find out the electric flux through this plane if the charge given to the inner cylinder is capital Q. Now see, the flux through these two planes, that means this one and this one, you have to find out the flux. This region and this region, you have to find out the flux. So whatever I am drawing here, these arrows are not flux line. I mean, there is nothing called flux line, because these are just, I am indicating the region. I have to find out the flux, and flux is a scalar quantity, not a vector quantity, and the electric field also is not this one. Now the electric field on this part is 0 because there is no charge inside, so there is no electric field line that will cross through this. The electric flux will only be via these two because the inner cylinder is there, and due to the outer cylinder there will be no flux on this plane. Okay, only due to the inner cylinder will be there. So inner cylinder, the charge that is given, that is capital Q. Now we'll see. Now let's say this is a cylinder having linear charge density is lambda. That means per unit length, the charge that is the cylinder containing, that is lambda. Then at distance r from the center of the cylinder, the electric field will be lambda by 2 pi epsilon naught into r, which is a function of the distance from the center of the cylinder. So here also see, I mean, I'll calculate the flux for one side, then I'll multiply with 2 to find out the total flux through this plane. So let us consider the top one. So this one we'll consider. So these are similar, so we'll just multiply with 2 to find out the total flux ultimately. So see, ultimately this is my region of interest, starting from the inner cylinder, ending at the outer cylinder surface. So each and every point, it is having different distance. So see, if I go from inner cylinder to the outer cylinder via this plane, each and every point the distance is different from the center of the cylinders. So each and every point the electric field will be different. At the same time, the electric field will be making different angles with the area vector of this plane. Now let us draw one general or random angle theta, which is of course crossing through this plane, and this distance of this plane from the center is r. Then what is going to be electric field and line? The electric field line will be radially outward. Electric field line will be radially outward, and the strength of the electric field line or strength of the electric field will be lambda by 2 pi epsilon naught into r. That is varying with the distance from the center. So lambda will just put, that is Q by L, or the charge per unit length, 2 pi epsilon naught into r. But here in our problem, the epsilon naught we have to multiply with 5 because it is filled with dielectric of dielectric constant 5. So we have to just multiply with 5 into 5 into r. Into 5 into r. So ultimately I am getting the electric field as a function of the distance from the center, that is this one, E. Now see, this is the direction of the area vector, small area vector dA, let's say at this point I will. So this is the angle between the electric field line and the area vector. So what is going to be the flux? D phi is going to be E dot dA, but the angle between E and dA is theta, so we can directly write E into dA cos theta. Now what is dA? Now if I vary the angle by very small angle d theta, I'll be able to find out one very small differential strip which is having the area of dA. Now we'll draw a bigger image. So let's say this is our image. This small angle d theta, it is having distance r from the center of the cylinder. Now this is radius r, so this will become r d theta. r d theta. And this is the area vector direction dA, and that is how the electric field is crossing this small differential area, making angle theta with the area vector. Now dA, or the differential area, this width I have to find out, then I have to multiply with L, because L, I have told you that figure 1 you have to imagine, or you have to keep in the mind that figure 1. This width I have to multiply with L in order to find out the differential strip area, because you have to imagine that this is the top view and the cylinders are kept like this. So this is the length of the strip is L. So L into this width will become our differential area. So what is this differential area? So I have to find out this width. Now see, this is, let's say, angle theta. So this is also becoming our angle theta. At the same time, if this becomes angle theta, then this is also angle theta. That I have assumed that angle between E and dA, this is also angle theta, because this is just opposite angle, this one and this one, just opposite angle. So this is angle theta, means this is also angle theta. Okay. Now what is this angle? Because this one I know, if I find out this angle, I'll be able to find out the width from the right angle triangle. If this is theta, then this is 90 degree minus theta, and if this is 90 degree minus theta, it is also 90 degree minus theta. If this is 90 degree minus theta, this is 90 degree, so this angle is becoming our theta. So on this right angle triangle, this is the hypotenuse you have to find out, and this is r d theta. So what is the value of the hypotenuse? R d theta by cos theta. Or you can tell that the component of hypotenuse in this direction is r d theta. So the hypotenuse value is r d theta by cos theta. So dA, so I'll find out, I'll put the value of E, 10 pi epsilon naught r. dA is r d theta by cos theta, and I have told I have to multiply with L in order to find out. So L I have missed here, so L I'll put. L I have missed here, yes. Okay. So cos theta, that is d phi. Now phi will be just integration of this, but before that let me cancel out some terms. Cos theta will ultimately cancel out. R will ultimately cancel out. L is also cancelling out. So it is becoming Q by 10 pi epsilon naught into d theta. Integration of that from the lower limit to upper limit. And what is the lower limit? You are starting from here. That time what was the angle made with the center with respect to the horizontal direction? See, this is 2r. This is root 2r. This is r. So this angle will be 45 degree. So this bottom limit will be pi by 4, and the upper limit will be when I'll end here. So that time what is the angle it is making with the horizontal direction? That is this angle. This angle is, this is 2r. This is r. So this angle is 60 degree. So it is pi by 3. So these terms are constant terms. Q, 10 pi epsilon, or only variable is d theta. So phi is the flux through one side, that is Q by 10 pi epsilon naught integration of d theta. It is theta, that is pi by 3 minus pi by 4, so pi by 12. So Q by 120 epsilon naught. Pi is cancelling out ultimately. So flux through one side, that is Q by 120 epsilon naught. To find out the flux through the entire plane, you have to multiply with 2, because other side also there is one portion of the plane existing. So phi total is twice of this, so it is Q by 60 epsilon naught, and it is matching with the option C. So our answer is option C.